We will be solving problem 783 from our statics textbook. This is just an overview of the approach taken. First we'll solve for the support reactions at A. Then we will determine the loading equations for the distributed loads. Then we'll integrate those equations to get the shear equations. Moving on, we'll integrate the shear equations to obtain the moment equations. And finally use all that information to draw the shear and moment diagram. And of course our final step would be to check for our solution. So first we start off with a free body diagram of the entire structure for this problem. We have the distributed loads on the left and right side, and by inspection you can tell that a couple moment is required on the beam to keep it in equilibrium. First we do the equation for force equilibrium in the x direction, which yields a support reaction of 0 in the x direction. Then we do force equilibrium in y direction at A, in y direction for the beam, which yields a support reaction of 0 in the y direction. Then we move on to moment equilibrium, and here's a simplified diagram which shows the distributed load as each of the distributed loads as resultant forces on the beam. Notice here we've added a couple moment at A to account for moment equilibrium. So here's the equation, and finally we get a couple moment of negative 24 kilonewton meter at A. Moving on to step 2. Here again we have the free body diagram for this problem, and here we have all the support reactions included as well. Here we've just presented the diagram in a more intuitive way, so the forces acting downward are actually negative and forces acting upward are positive. When we move on to the algebra and figure out the slope for the distributed load on the left, which is negative 8 over 3. Then we work out the constant, which ends up being 0. So finally we have a loading equation for the load on the left. Similarly, we find the equation for the load on the right, and here we just use some common sense to figure out that the load on the right is actually the load on the left shifted by 6 meters to the right, and we account for that by including this factor of negative 6 in the equation, which finally yields this as the equation for the distributed load on the right. Moving on to step 3. Here we'll be integrating the equations for the distributed load to get the shear equation. Keep in mind that this integration, it only yields the equation for the change in shear. We will eventually have to account for any point loads, but we'll get to that later. For the distributed load on the left, here's how the integration works out. You finally get a change delta V1 is this right here, and since we don't have any point loads, V sub 0 is 0. Therefore we get the shear equation as such. For the distributed load on the right, again we work through the integration and get this as our equation. Keep in mind the limits for this integration. It is from 3 meters to variable length x, and again there is no point load here, so V sub 0 is nil, and which yields a shear equation of this. Moving on to step 4, we use the shear equations that we've just calculated to calculate the moment. Again, this is the relationship that is used, and to find delta m, and then we will eventually find m using this equation. For the distributed load on the left, this is how the integration works out. This is the expression for delta m. Notice here that there is a point moment, couple moment acting at point A. Therefore, we have to account for that using this factor of plus 24, according to this equation right here. So this is the equation we get for moment for the internal moment at for the distributed load on the left. Similarly, we work out the math for the load on the right, and this is the expression we get for delta m. Again, we need to account for initial moments according to this expression here, which is the negative 12 from the distributed load on the left and the plus 24 from the couple moment acting at point A. So taking all that into account, we get an internal moment equation of which is as such for the distributed load on the right. So we figure out the equations for the distributed load, we figure out the shear equations and the moment equations, and we use all that information to draw the shear and moment diagrams. This is how the shear diagram turns out, and this is the moment diagram, and that's the end of the problem. But before we wrap up, we'll just do a quick check to ensure that we've got this problem right. First, you can see that there is no shear discontinuity, and this makes sense because shear discontinuities occur only when there are point forces acting on the beam. In this problem, there are no point forces, therefore no shear discontinuities. For the moment diagram, however, we do have a couple moment acting at point A, and therefore we have the moment, the internal moment equation or the diagram starts with a y-intercept of 24. But notice that there is no couple moment at the free end, therefore the moment is 0 at that end. And for the third point to check, we note that the moment equation is 1 order of magnitude higher than the shear equation. The shear is quadratic, whereas the moment is cubic, and that also makes sense physically. So we've solved the problem and we've checked it, and that is all.